Thanks for the opportunity. I'm kind of sorry I can't be there in person for reasons I don't really want to elaborate on. Otherwise, I'll just get angry. So I'm going to talk about mostly variability today. I'm going to present some work which was led by my former PhD student, Hansel Lee, who's currently in Leuven. And this is also in collaboration with David Marshall, James Madison, and my colleague Wang Yan at HKUST. So here we're going to be talking about eddy-driven variability. So there is some sort of eddy-mean interaction things going on here. And the practical problem at least I'm interested in, is that generally we know the coarse ocean resolutions have a fairly damped representation of variability. So the question is, can you somehow recover this by updating your parameterization, and in particular, in this case, the mesoscale eddy parameterizations? So since this is an overview talk of sorts, I will say a little bit more about what kind of the climate models and biases in the mean and variability. So usually I talk about the mean, so I'm going to try and talk about variability today. In particular, what's the role of the resolution and the parameterizations? Then I'm going to get to the work. I'm going to sketch out the work we've been doing on trying to derive the intrinsic timescales associated with eddy-mean interactions. I'm going to derive a low-order, or at least sketch out how you would derive a low-order dynamical system, which is based on a previous paper by James Madison. You end up getting something like a nonlinear oscillator model with, it's a bit like Locker-Volterra, actually. Then once you can get that, you can get implied oscillation and decay timescale. For this particular talk, I'm only going to be talking about the oscillation timescales. Then we will try and proceed to see if we can find these things in more complex ocean type models. It's going to mostly focus on the 100-layer gamma desiccant model because it works beautifully there. Going to be a little bit more skimpy, I suppose, talking about the Nemo model, but it doesn't really work there for reasons there are various reasons, and we're trying to figure out what the exact reason is. Okay, so I think Pascal mentioned quite a few of these already, so I'm going to be kind of fairly quick in the overview of this. So fluid dynamics fundamentally is a multi-scale phenomenon. So you've got motions occurring at the kind of over a whole spectrum of scale. So you've all the way from kind of low frequency or long time scale, large space scale motions, all the way down to things like mesoscale eddies, some mesoscales, near inertial waves, I guess is here. And then there's you get small scale mixing and so forth. So long story short, I think the way at least I think about it is you can think of these if you really want to, as each of these individually might be some sort of pendulum. It wants to oscillate in some way once you start forcing the thing. The problem is that they don't oscillate independently. They tend to oscillate within a coupled sense. So either you have a pendulum which is coupled to other pendulums, or you have a pendulum which is charged, and then the different charges will start interacting with each other and so forth. So ultimately, if we're talking about climate modeling, we're somewhat interested in the large scale. But this one then, so what kind of large scale response in terms of the mean or the variability would depend somewhat on what you do about these smaller scales. So it depends on how you model the large scale circulation, which in turn depends on how you model the mesoscale eddies and so forth and so forth. So it's a complicated problem, essentially. So in practice, what you might want to do is you just want to throw resolution at it. And we know what the equations of motion are. You try and throw resolution at it, and then you examine the response. In practice, you can't do that. So as Pascal mentioned, so some of her simulations are going down to on the meter resolution. Something that we can probably achieve more, at least from a global point of view, is maybe 12 degree, maybe now slightly higher. So 12 degree was kind of state of the art 5-10 years ago-ish. The kind of computation cost we're talking about in terms of CPUs for 12 degree is that if you give me the whole computing resources at a research intensive university, say 4,000 CPUs, I can give you one 300-year run in 1 year. So that's the kind of cost we're really thinking of in terms of a 12-degree global resolution model. As you may know, if you double the horizontal space scales, then you are increasing the degrees of freedom by a factor of 4. And then for time stepping reasons, stability reasons, you probably want to reduce your time step by half. So already you're increasing the computation cost by a factor of 10 or so, and you haven't talked about the vertical either. So in practice, the 12th degree is not really what we use routinely. The workhorse remains the 1 degree or the coarser degree in the coupled climate models and also in the long-term climate projections. So 1 degree I can get maybe 100 years a day on a few hundred CPUs, so it's much more tractable. But of course, then the problem in the 1 degree is you don't have your mesoscale eddies. You don't have these kind of small fluctuations. And in a quarter degree, you kind of have them, but you have to be a bit careful. It might be a slightly weird representation of these things. So again, going back to the previous slide, so how you model these would presumably have a long-term or would have a kind of nonlinear impact on things like variability in the mean state. So these kind of things depend on resolution and depends on how you do the parameterization. So in the 1 degree, you don't have these mesoscale eddies. So somehow you need to write the effect back in whatever sense you want it to mean. One way to do this, one standard way of doing this is what's called a GM scheme. It's not the only one. There are many other things. This is not all that baroclinic mesoscale eddies do. So the GM scheme essentially is it looks like a diffusion, at least in the QG sense, but it's really an advection. So what it's trying to do is you got some front, and it does it in a certain way. So the eddy-induced velocity here wants to flatten the front in some sort of kind of moment-conserving sense, adiabatic as well. It looks a bit like thickness diffusion. It's not exactly thickness diffusion. And there are many good numerical things about it. So most ocean GCMs nowadays tend to have some sort of form of GM in. So even Oceanography, I know, has now recently put in some kind of GM/isoneutral diffusion in, even though they were thinking of going eddy resolving. Once you have this, then of course the problem would be that if you really think this is a good form, then what do you do about this extra parameter you need to specify? So this would be parametric uncertainty. Or you might even go to say, well, is this form even a good one to use? Or is there some sort of structural uncertainty related to this parameterization? So this is kind of an ongoing field in things like machine learning and so forth. So the one I will be talking a little bit about today is, at least the thing I would be doing is proposing a certain form of GM, and then we'll start looking at what kind of response you would get. All right, so where are we? So now let's say, so we're supposed to be talking about mean and variability. So let me kind of say a little bit about at least how I interpret what they are. So the problem I came to when I was writing these things 2 or 3 days ago, it was that I don't really, in some ways it's actually, if you see it, it's kind of obvious. It's a bit like turbulence. You see turbulence as turbulent. But to actually pin down what it is not so straightforward in some sense. So normally in statistical physics, how we would do this is that you take a whole load of realizations, you take an average, and you call the ensemble average your mean, essentially. Then your variability would be your deviations away from that mean. Normally, that's what we would do. The problem, of course, is when you do simulations, if you run ensembles, that's kind of expensive. And if you do observations, we don't have multiple Earths. We only have one Earth. So we don't really do ensemble means as such. So usually what we do tend to, or at least you try and link up the long-term mean to be like the ensemble mean, and you talk about the mean as the long-term mean. So usually this is making some sort of what's called ergodic hypothesis, which is not true probably, but that is what you do. But if you take this one, whatever long-term then you have to define what you mean by long. But then this thing evolves on the long, it presumably evolves as well, right? If you're not at equilibrium. So then variability is a little bit of a kind of sticky, is a bit of a not entirely well defined. I mean, so you know what it is, but then to actually nail it down is not so clear, at least to me. So there are things to do with the eddy field, which is a fluctuation of some description. So the eddy field or the eddy kinetic energy. So that's one type of the statistics related to the variability. But then your model state could also evolve around the mean in some way. So if I draw a figure, it might be easier to talk about what I mean. So here I have some sort of model transport and the eddy kinetic eddy energy. So the mean could be a horizontal line. So then I'm talking about, then if I take that mean, then I'm talking about the variability about that equilibrium point. Or somehow I could say that my equilibrium point is the blue line, or at least some sort of low pass of the blue line. Then the variability is whatever is on top of that. So the thing I want to talk about today is the first one, not the second one. So I'm not going to talk about the small scale fluctuation. I'm really thinking on kind of decadal or multi-decadal long time evolutions of the model state. And that's what I mean by variability in this case. And here I'm going to be focusing on things relating to baroplanic eddies. So fundamentally, at least from a process point of view, we think these should occur on a long time scale. Because this would involve some sort of deep ocean adjustment. So we're not really thinking of things on the seasonal or the kind of seasonal interannual timescale, but longer than that. Of course, as Pascal mentioned, then of course, these kind of things could be modulating each other. So your small scales interact with large scale, and your large scale can modulate what your small scale has. Not going to talk about that today. Just only going to be talking about decadal eddy-driven variability. So for these kind of things, you care because you want to distinguish, for example, natural and anthropogenic variability if you're doing climate forecasting. If you have a model that doesn't represent the natural variability in a fairly convincing way, then how can you really say whatever you're seeing is not, in fact, just natural variability? So that's an issue we have in kind of climate predictions. It has impacts on the long-term evolution, presumably. So this is a quick advertisement. So I have a funded project with Marina Levy at L'Océan, which is to look at ventilation, essentially. Mostly heat and carbon. It's going to look at oxygen as well. So the idea here would be that because your eddies are going to impact the stratification, that's going to impact your ventilation, and in particular the deep ventilation. So once you go past the next layers, you're in the realm of the deep ventilation. You can affect the ventilation pathways, and that would have an impact presumably on your kind of heat budgets, or kind of what kind of heat or carbon or oxygen signature you might be getting. And it's generally known that one of the big problems in, I guess, the anthropogenic carbon sink is the modeling of the decadal variability in the Southern Ocean. And so the Southern Ocean is a particular place where anthropogenic carbon uptake is large, is fairly significant. And it's known that the climate models tend not to do that very well, at least it doesn't represent the decadal variability very well. In the eddy resolving or eddy rich ones, there actually is much better. So we think it's something to do with the resolution or the parameterization of the eddies there. Or more from I suppose from a theoretical view, we're interested in saying, well, so what kind of variability do we have? What's the mechanism behind these? Do they modulate each other and so forth? So that's kind of the, I guess, motivation for studying variability if you've never seen these things before. Okay, I was going to talk what kind of things affect the mean and variability. There are many things, but the one I'm going to focus on is the model resolution parameterization. So generally, we know that you can throw resolution at it, then you tend to improve the mean and variability. Yeah, you get a substantially larger signature in the variability, and the mean tends to be better. By better, I mean closer to observations. You can't do that arbitrarily because it's really expensive. So there's a limiting factor in the complexity scaling for these things. So they go like order magnitudes for doubling of the resolution. So you can't do this routinely. The coarse resolution models have a strong bias in both, particularly if you don't do parameterization. If you start doing parameterization, that tends to improve some of the mean, but you probably don't improve the variability. So that's not entirely a surprise, right? Because your coarse models don't have any eddies or don't have any small scale fluctuations. It's going to be really stiff. So anything you have on the variability gets damped out at the grid scale, probably, which impacts on other things. The eddy permitting ones tend to, you expect it to improve on the variability. Sometimes that's known to give you different biases for the mean. You improve it in some places, but you degrade it in others. Right? It's a little bit of it's like whack-a-mole. You smack one down and then another one pops up. Or it's like debugging. You fix one bug and 150 other ones pop out. So these are known problems, and when we have ways to kind of try and target those, the problem is you can't tune them separately. You can't kill one without touching the other one. Both of them interact with each other. It's generally known things like GM and Ready end up damping the variability. damping the variability in the sense that it makes the model stiffer, and it also makes the things like the eddy field substantially less energetic. We know reasons for this. There are ways around this, which is not what I'm talking about today. So Carsten has one, which is the biharmonic GM, for example. I have one which is on the field splitting. Stefan and the US group have things on backscatter. And these, again, they can improve variability, but they also impact the mean. And it's an open question on whether you can tune them separately or how you would tune them both or have a model that represents both. The one I'm going to be focusing on is number 2. So the question here is that can we in fact get some sort of variability representation with a coarse model, even though I just said that, that's the traditional approach will probably not give you that. All right, so what is the eddy-driven variability, at least from our current understanding? So the mechanistic pathways is somewhat known in this case. It actually dates back to Hock and Blundell and probably earlier. So the idea you have is that your wind, suppose you just have a constant wind forcing, so that's going to drive a mean. So the Ekman transport is going to tilt your isopace nodes, so that's going to steepen your mean. Once you steepen your mean, your background state, your mean, your model state, let's put it, and that's going to lead to baroclinic instability if you have eddies. So you're going to start driving up an eddy field. The eddy field wants to slump the mean. So at some point, there was some inertia of the eddy field as it grows up. As it becomes energetic, it starts damping the mean field. Once the mean field damps, there's nothing fueling the eddies itself. So the eddy is going to start decaying in some sort of natural time scale. So once the eddy field dies, then your wind is going to start steepening the mean again. So it isn't, and then the cycle possibly continues. Of course, if you have a very stiff system, it might just go straight to equilibrium. But if you think you have a loose enough system, then you would get this kind of periodic cycle or limiting cycle behavior. So it's a bit like the predator-prey models. In the predator-prey, in this case, the mean would be the prey and the eddy would be the predator. So your prey population grows and that leads to, and then your predator eats the prey that grows, and then at some point your predator is eating too much of your prey that dies, and then the predator dies and it undergoes this kind of competitive limiting cycle behavior. These kind of things happen in the ocean. It happens in kind of self-limiting behavior kind of phenomena, like in the atmosphere, you've got these storm tracks. In plasma physics, you've got these zonal-flow formations. So somehow your turbulence ends up driving a zonal flow, and then the zonal flow suppresses the turbulence. So these kind of things are important in fusion. Or generally, I think someone just talked about the layer formation. So once you have your open field, you have a certain place where you do you have a preferential place to do the dissipation that forms your layer interface, and then that becomes more and more preferential for the dissipation. Then you end up forming these layers, and it ends up arresting some sort of arresting some of the phenomenon. So if we think that is the energetic, that's the kind of mechanistic cycle, then previous work have essentially diagnosed the energy cycle associated with that mechanism, and they find it's consistent, and it turns out to occur around the decadal timescale. So this work by Hock and Blundell would be in a 3-layer QGCM model, is a QG model. They force it with, there's some sort of realistic topography, and what they find is that the energy cycles goes in kind of decadal periods. Whereas some kind of decadal, if you take the power spectrum, I guess it would have a peak around the decade period time scale. This is a channel model, and similar things have been found in work by Chris Wilson in 2015, and also in a primitive model by Sinha and Abernathy. This would be in MIT GCM, and all of these are channel models. They do these in ensembles because these are eddy permitting or resolving calculations. So they find this in the ensemble calculations. All right. And then similar work has been, analogous work in global type eddy permitting calculations have also found similar things, and they call it the Southern Ocean mode. So these are work coming from Henk Dietrich's group. So there's this one, the Labas et al. 2016, they call it the Southern Ocean mode or the SOM. So they run the POP model, I forgot what the resolution is. I think it's 1/10 over like a centennial timescales, and they find you get these multi-decadal variations by analyzing the EOS and so forth. So this thing happens in the Southern Ocean, but it also has a signature in and has a long range signature. So they find that, for example, it has an impact on the Mach. And they also find that you only have this in the eddy-rich experiment, and the energy cycles are consistent with what was just described. And it's not entirely surprising, right? Because in your coarse resolution model, you don't really have the eddy energetics, and you don't really have eddies either. So maybe it's not a surprise you don't really see that kind of signature in the eddy models. And there's a recent work by Smulders et al., which is also from Henk Dijkstra's group, studying what happens to these kind of things if you are under a Mach collapse regime. All right. Okay, so that's 20 minutes of outlines. I'm going to get to the things we actually did. So the question here, the overlying question is, so previously people have found decadal or multi-decadal oscillations in a eddy-permitting model. You have an explicit model of the explicitly resolving the models in some way. Can you in fact get something like this in a coarse resolution model? So you can imagine the standard wave, for example, if you do GM and constant, then your kappa, so your eddy-mean interaction is kind of fixed in some sense. Then of course you're not going to get this, or it's very unlikely you're going to get this. But that's for the standard GM. So if you allow the GM to be time varying and possibly spatial varying, then does it somehow relax in some way? The second part would be that the previous works have found that you probably want some sort of energy cycle. So maybe you want a GM kind of scheme which is constrained on some sort of underlying subgrid energy budget a bit. So essentially under the remit of TR181, right? So that's basically where we're going with this. So we're going to look at, there's a particular scheme called the geometric scheme, which is an eddy energy constrained parameterization. So we're going to study what are the implied timescales if you use the geometric parameterization. You can do analogous work with things like the mixing length type thing. I'm only going to talk about the geometric stuff today. I was going to derive a low order model first to see what you can get from, what kind of information you can get from a very idealized but coarse model, just to see if there is in fact anything to look at. If there isn't anything there, it's very unlikely there is something in the more complex models. So these models are essentially similar in spirit to the Sinha and Abernathy one, which is based on energy cycles. There's one, so Remy, I think, is in the audience. So there's one Remy's involved in, led by Lenk and Novak. So this is on atmospheric storm tracks. There's one by Eli Ong, which is on, so they use it to model the Antarctic slope front, but the ideas are basically the same. So we first started doing this work so we basically have a result back in 2018, and we just sat on it for 6 years and didn't do anything with it. So this is kind of an extension of the thing we sat on for a few years. Somewhat related to the work on eddy memory, but it's very different. So the eddy memory talks about having some sort of decorrelation timescale. So you talk about some sort of decorrelation kernel. Led by Georgi Manicharian and Wissam Moon and Henk Dijkstra. So the one we're going to do is a dynamical system model. And it's basically Madison et al., which was published last year, but coupled to a basin. So I'm going to only sketch out how you derive this. For those of you who know about these things, this is just a Galerkin projection of the mass conservation equation. So what you do is there's a channel length and basin length or something. We leave it as a parameter for now. There's a channel basin boundary, and you assume the density essentially is, I don't know if you can see. So it's sloping in the channel and it's flat in the basin. So there is some sort of connection in between the two. The linear slope is dependent on this M. So this is the thing that is going to be time varying. So we assume a particular form of the rho, and now your time dependence is on the M. And we're going to do the projection on the rho, but it's actually going to be on an M. So within the channel, we're going to make the assumption that this is driven, this is essentially mass conservation equation. So you have your density, which is conserved. This is zonally averaged. There is some residual velocity, which is in this case, your Ekman, and also your eddy-driven velocity, which is going to be modeled by the GM. Your densities can be moved around. If you do not assume this kind of form, then what you have is you get these kind of curves, but we're going to make make an assumption to simplify the model so that everything is just linear. So you're just assuming, you're just working out how these things move around in the linear sense. Rho is the appropriately interpreted density. I think is strictly speaking the McDougall-McIntosh residual TWA thickness weighted average velocity densities. So you take this form, you take this thing, and then you do a Galerkin projection. So Galerkin projection is like how I think Leo talked about something like the Lorentz equation yesterday. So you start with something like a PDE. So normally for Lorentz, well, the original Lorentz would be what I think is Rayleigh-Baynard, right? So you take there's a stream function, vorticity, and temperature, and then you expand it in Fourier modes, and you say that anything which is larger than wave number 1 or 2 you throw away. So then you end up getting a 3-dimensional dynamical system. So that's a projection onto the Fourier mode. So here we project onto the linear mode. So by projection, what you mean is you just take integral and you multiply it by the linear pi, in this case, the y. So this is the basis, essentially. Then you have to do lots of integrals and do some kind of nasty things to do with, well, you have to do lots of integrals. You simplify it by assuming a certain form of the forcing and the eddy and the mean forcing, or the wind forcing. So the wind forcing goes like an Ekman overturning. So if you've got your density surfaces, you're twisting these things up. Or, from my angle, it's twisting up, but from your, it might be twisting down. So steepening isopycnals. Then the GM stuff is trying to flatten it. So you have a competition with this, with the steepening and the flattening. And this is going to be dependent on this kappa GM parameter. So you take all of this, bung it into the equations of motion, you do lots of integrals. These are basically going to be delta functions, so the integrals become a little bit simpler to do. And after a whole load of tedious algebra, you're going to get some equation in M. M is your linear slope, so you're going to relate that to the baroclinic transport by the thermal wind relation. So somehow you're going to turn this into T with some F naught over N factors, F naught over, or rho naught factors, sorry. In the end, you get this kind of thing coming out. So there is some sort of Basin factor, which is a lengthening. So it's reducing the transport tendency. There's a tau naught, which is your wind, and then there's your kappa GM, which is here. All right. So the usual thing when you have a system like this, you look for the equilibrium. So the equilibrium, if you just have this, for fixed tau naught and kappa GM goes like tau naught over kappa GM. This one is not entirely surprising, right? Because if you fix the eddy interaction, then the larger your wind, the larger your transport. And then the more you flatten, then the less your thermal wind, so the smaller your transport. So this one's kind of well known. But we want to somehow increase the complexity of this. We want to somehow have a form on how the kappa GM is going to be T dependent. So for the eddy energy, we might expect it to go like some sort of evolution. So there's the baroclinic conversion term. This would be the W prime and rho prime term, essentially. And then some dissipation. On the coarse, sufficiently average, we're going to make the assumption that advection and non-locality is not going to be hugely important. So that gets averaged out. So that's not going to be the dominant term. And then now what you have to do is you have to give it a scaling for kappa GM. You have to say whatever this is, or maybe you don't, it doesn't really matter. So in this case, what we do is we take the geometric scaling, which is given by this guy. So if you want to see more, it's in the Marshall et al., one of my older kind of recent papers. So this is a scaling for Marshall et al., and then a choice would be how you do the energy dissipation, or at least what's the energy flux of what you might call the mesoscales. Here we take a linear damping. I'm not going to really justify why. Well, it's mostly because it's simple, but there are other reasons for this. So then the idea is you put this back in here, then the D is going to be some dissipation. Your M is going to turn into some sort of factor of T, and then you rearrange accordingly. Then what you get is, once you do some tedious algebra, you get this kind of thing coming out. So you have a two-component dynamical system. There's a T which evolves according to something, and then there's an E that evolves according to something. So this is a two-dimensional dynamical system, a whole load of things you can do with this. This ends up being a nonlinear oscillator model, essentially. It turns out it has a Hamiltonian form if you take E naught to be 0. So E naught is like some sort of is maintaining some sort of base level energy. If you don't have that, you can actually do a coordinate transformation, do a variable transformation. You get a Hamiltonian out of it. So E naught here, even though it's a source, it acts as a damping for the oscillations. And one of the things I would try and remind me if I don't talk about it is really the breaking of the Hamiltonian form, which actually gets rid of your variability. All right. So suppose you don't have E naught or you have E naught, you can go ahead and do the algebra. In this case, the equilibrium goes like this. So the thing to notice is that your T star is tau dependent, so it doesn't care about the wind stress. This is related to the phenomenon of eddy saturation. What you're basically doing is that you increase the wind, but then when you increase the wind, you steepen you make the eddies more energetic in such a way that the steepening effect of the wind and the flattening effect of the eddies end up canceling out, so your transport doesn't change. But it does depend on the lambda and the alpha, so it depends on what you do to the energy. And then similarly for the energy, then the energy depends on the wind. So the larger your wind, the more energetic your field, even though there is no change in the mean as such, at least in the equilibrium. So one of the things to note is that under this kind of framework, where you can derive some sort of nonlinear oscillator model type model, the mean equation determines the eddy state, and the eddy equation determines the mean state. So this is a particular feature of geometric, and we just need to go with this. In the previous paper, Madison et al., what they find is that if you make it Hamiltonian, then the Hamiltonian form is actually robust under stochastic forcing. So what that means is that your period of oscillations, you have to think of it in terms of expectation, but it actually does, it's entirely preserved under stochastic forcing. So you don't have to have it deterministic. All right, so we have the system, and then now you have a low-order dynamical system. The usual way is you take the equilibrium, you linearize against the equilibrium, about the equilibrium, work out the eigenvalues. In this case, the system is 2 by 2, so you can actually do things by hand. The eigenvalues has a real part in the imaginary part. The real part gives you a decay or exponential growth. The decay timescale is given by this guy. The real part is given by this thing. Sorry, the imaginary part is given by related to this thing. If you make the assumption that the decay timescale is very long compared to the oscillation timescale, which if you take some estimates, that's actually true, then you can simplify the oscillation timescale and you get, ignore the factors, but the main one you get is this thing. So it's implying there's a scaling of the oscillation timescale that goes like alpha, LB, and tau naught. So LB is the basin length. So you might suspect this. So LB that's a particular LB. So the larger your basin, then that acts more as a brake to what kind of oscillate. It takes longer for you to do the adjustment. So then you have a longer oscillation timescale if you only force over the southern ocean. The main difference here would be the time. So what is it? If you put in kind of southern ocean values, which we took from a previous paper, then you get implied timescale about the multi-decadal period of 30 years or so. This is different to the one where you have no basin, then it's more on the decadal timescale. So this is so at least the low order model suggesting you should have something if you use geometric. So that's where we're going to go with the rest of the talk. It's just going to be me showing where it works and where it doesn't work. So the model is suggestive, but does it actually show in the more kind of real models? So the first one we did was we try and mimic the dynamical system model somewhat, but not exactly. So it should be obvious that if you time step the dynamical system model, you will get what you just derived. So it's not a very good test on that one. So here what we do is we take the 100-layer Ganodesican model. So it's so the 1-layer Gann is like a box model. So what you do is you have your thickness of your layer, which depends on the input from your Ekman flow, and then some sort of residual Ekman flow, your eddy flow, your dipycnal mixing, which is a cross-layer transport, and then some NADW, something that you model as an NADW or a North Atlantic deep water formation. So each of these evolve accordingly. So this is like almost an adiabatic model. It's not except for this QD, but it is a box model. So this is going to be 100. Is going to be 100 dimension dynamical system, which you solve numerically. And then we have we use exactly the same forcing as Marshall and Zanner. So they propose some sort of vertical form, and that's and then the eddy part is parameterized by GM, essentially relates to the magnitude of GM. So how we're going to do this is we're going to modify it for this to include geometric. So what you have is you've got your kappa GM. We know what the scaling is, but in the original model, what you have is you just have the thicknesses in the basin. So what we assume is that you have a linear slope. We fix the outcropping, so you're making the assumption that all the outcropping is at the same location. Then, depending on your layer depths, you know what your density field is, at least from the linear sense. That gives you your m squared. The n is implied by the basin model, by whatever's in the basin. You interpolate it accordingly, then you have all the things you need to time step an energy equation. So you get implied m and n squared, you get some sort of Southern Ocean integrated eddy energy equations. Again, we ignore the advection and diffusion type contributions. Then you have a kappa GM, which is going to be essentially coupled to an energy equation, and that is going to be some sort of representation of the eddy-mean interaction. So your mean is going to drive the energy evolves, and that's going to feed back onto the mean. And from the previous analysis, we expect that there should be some sort of decadal, multi-decadal type oscillation if you start changing your wind forcing, which is going to be reflected here. All right, so what we did was the procedure is you spin it up with a kappa constant just for numerical stability. So we couple our energy even though the energy doesn't do anything. It's just to spin up the energy equation, otherwise you get some sort of exponential adjustment. It's not very stable. You do a minor spin up just for stability reasons, and then we do a 3,000-year spin up of the control. So for this model, it takes about 5 minutes. If you didn't have geometric, it takes even less than that. It's like a minute or so. These models are very fast to run. Once you have a spin of a control, then you take a control and then you run it for another 3,000 years to get your different equilibrium. So here, when I talk about equilibrium or the mean, I really mean this endpoint. So I have a well-defined equilibrium in this case. It really is an equilibrium. I'm very specific in what my equilibrium is. It really is the long-term equilibrated state. So just from looking at this is one representative graph, and you show that 3,000 years is basically enough to give you a good representation of the equilibrium. Once you get to all of these, then you do an oscillation experiment. So we force it with some sort of harmonic forcing. So your Ekman transport is going to be oscillating around 10% around the base value with some period. And then we run 500 years of those. Then what we want to know how the system responds. So this is like a standard thing to do. You take a system you don't know, you smack it a little bit and just see how it rings. So here we're trying to see how it rings. Where it rings the loudest would be where we think the resonant timescales are and where the intrinsic timescales would be. So an example of this would be, this is a 40, 60, and 80 years. So 60 is going to be what we diagnose as the resonance. And what you find is that there's a very large amplitude response, a much larger amplitude response at the 60-year compared to the other one. So that seems to indicate there is a resonance going on. If you do this as a phase portrait, then you find that the 60-year has a much larger radius or effective radius. So this would also be consistent with like some sort of resonance feature. How this works is I think it goes, the mean increases, then your eddy energy increases, then your mean gets killed off, and then your eddy gets killed off. So it's going anti-clockwise in the phase portrait. Then what you can do is you can diagnose a resonance. So the way we did this is using what's called linear response. So you take your 2-time series, take a FFT of those, divide one over the other. So the response over the forcing. But you take it only at the forcing period, because otherwise you end up you need to be careful about dividing by small numbers of zeros. And then the ratio of that, the real part is called a gain, which is your real response, and then the imaginary part is called a phase. So that is whether one signal lags the other or vice versa. If you do that, then the geometric one gives you a ringing for this particular control experiment at 60 years. So we get a multi-decadal sort of resonance, so that's good. And then you have some phase lags, which are the phase behavior changes depending on once you pass the resonance or before the resonance. If you use this with a constant GM, you don't get any of this. So that seems to be suggesting here that geometric is one of the things that gives you some sort of timescale. There's an implied timescale associated with geometric here, which you do not get with a standard constant case. The caveat here is assuming it's a linear response. I can comment on that a little bit more later on. So I've got 5 minutes left, so I will probably skip this, go forward a little bit. So the cross correlation, the lag correlation, I'm not going to talk about. So then once you have that, then that's for one case. Then you can start doing this over the parameter space. So here we took sections over parameter space, and you diagnose the, what's the resonant timescale, which we're calling the oscillation timescale as a function of parameter. Because we had this prediction that it should go like LB alpha tau naught with the square root. So what we find is that if you increase your alpha, you increase your tau naught, then your timescale decreases. If you increase your LB, your timescale increases. So that's consistent. The exact powers do not match, and there's no reason it should match, I suppose, right? Because this one is for a really idealized model. And it doesn't match, at least for when you have a northern, this is a some sort of model for the North Atlantic deep water formation at 20 Sverdrup. So there's like some sort of Labrador Sea convection, which we don't have officially in this, we don't have explicitly in this kind of setup. If you switch that off, you get rid of that process, then you get the 1 over square root of tau, and you get the square root of LB back. So that's reassuring, I suppose. It doesn't work for the alpha, but quantitatively it doesn't work, but qualitatively it's going in the right direction. Decreasing with alpha and tau naught and increasing with LB. So it seems that, so basically, so this is the first hint that if you start adding other things, then it's going to modify stuff. But it would seem that, at least for this particular model, you still seem to get some sort of Hamiltonian or some sort of oscillatory type structure, which is somewhat by design. So then I'm going to be very brief on this one, because it doesn't work in this, basically. So you do the same thing in NEMO in a 2-degree model, and it turns out, in this case, I used the wrong wind forcing, which also doesn't help. The forcing is too weak. So the idea was we were going to run, again, equilibrium runs. So we do 6,000-year runs, and then we do 500-year adjustments. And similarly, 10%. But so the current runs I have presented use the wrong tau naught, wrong unintended tau naught. You do the same thing, and then the things are slightly different. So if you take the NEMO one, then you diagnose the Drake passage transport and the energy. Then what you find is that the energy lags the mean, which is good. And that's what we expect. What is not good is that your wind forcing seems to be very much in phase with the transport. And it turns out, having looked at the data yesterday night, most of the thing we're seeing is, in fact, a barotropic response, which isn't really what we want. But when we're talking about what we think is the eddy decadal variation, we're thinking of the stratification change, but the barotropic stuff has nothing to do with stratification. So there are more things that we need to do to look into this. If you look at the cross correlations, there is some suggestive evidence. There's some sort of regime transition between the 30-year or so. So maybe there is something, but who knows? This is a bit dubious, so I don't really want to say too much more about this. So the kind of long story short is we derive something. It works beautifully in a layered model. In this case, in the layered model, I guess it's still somewhat Hamiltonian, or this it's not very stiff. In the NEMO model, it probably is very stiff, and there's a lot more physics going on, which is probably breaking the Hamiltonian structure of the response. So as of yesterday night, when I looked at things like the AMOC diagnostic, so it looks like there is a response, but it is actually very weak. So it looks like geometric is implying, or at least allowing, some decadal variation, although it's very weak, possibly due to the 2-degree nature. You might ask, would you get this thing in a 1 degree or a 1/4 degree and so forth? But that's for future work, something to look into. I think this is my last slide, so I will probably just leave it here. If you have any suggestions of what to look at, particularly things like going beyond linear response, I would be quite happy. I can take some suggestions, actually. So thanks for your time, and if there's any questions, I'll try and answer some of those now. Okay, thank you.